This video is going to introduce the squeeze theorem, which is something that we can use when trying to find limits. So I have written on the screen a statement of the squeeze theorem. It says, if our function f of x is bigger than or equal to h of x and smaller than or equal to g of x, so the function we're working with is always between function h and function g, for all x in an open interval containing c, except possibly c, and if the limit as x goes to c of h of x and the limit as x goes to c of g of x equals L, then we can conclude that the limit as x goes to c of f of x is equal to L. And I have a picture over to the side trying to illustrate what this theorem is saying. This theorem is saying that if the function we're interested in, which is this red function in my picture, we'll call that f of x. If the function we're interested in is always smaller than or equal to another function, we're going to call that g, and always bigger than or equal to a third function called h. So the idea is our function lies between two different functions. And I can see on this picture that the limit as x goes to 0 of g is 0, and the limit as x goes to 0 of h is also 0. We can then conclude that the limit as x goes to 0 of f is 0 as well. So let's see how this works by doing an example. I want to find the limit as x goes to 0 of x times sine of 1 over x. If I plug my x value in, I get 0 times sine of 1 divided by 0. And 1 divided by 0 is undefined. I can't find the sine of 1 divided by 0. So just plugging that x value in is not going to work. So instead, we're going to use the squeeze theorem to try to solve this limit. So first of all, I know that sine of any angle has to be between -1 and 1. That's just the range of our sine function. If you think about the unit circle, sine is your y-coordinate on the unit circle. It has to be bigger than or equal to -1, smaller than or equal to +1. So I naturally have some bounds for sine of 1 over x. And then I'm just going to multiply this inequality by x. And if my x is bigger than or equal to 0, then I'll get -x less than or equal to x times sine of 1 over x less than or equal to x. So I know that the function I'm working with, x sine of 1 over x, always lies between -x and +x. Now, if my x value was negative, if x is less than or equal to 0, if I multiply this inequality by x and it's negative, the direction of that inequality is going to flip. And so I'm actually going to get -x bigger than or equal to x sine x, 1 over x bigger than or equal to x. Or if I want to write that in the other order, x less than or equal to x sine 1 over x less than or equal to -x. So I have the same bounds, it's just the function that's on top and on the bottom flips if x is positive or negative. And so what I'm going to do here is I'm going to find the limit of -x, which is my lower bound when x is positive, and my upper bound when x is negative. And if I find the limit as x goes to 0 of -x, I'm just going to get 0. I just plugged my x value in to do that. Then I'm going to find the limit as x goes to 0 of +x, which is my upper bound when x is positive, and my lower bound when x is negative. Well, that limit is 0 as well. And since both of these limits are 0, and they happen to be my upper and lower bound for both coming in from the right and the left side of 0, that means the limit as x goes to 0 of x sine of 1 over x is also equal to 0. And that's just an application of my squeeze theorem. In fact, the picture that I showed you at the beginning of this discussion is this function. So in red, this is actually the function x sine of 1 over x. You can't really tell in this graphic, but this function is actually undefined at the origin. And then I have the line y equals x, which is my upper bound on the right side is 0, and my lower bound on the left side is 0. And then I have the line y equals negative x, and I can see that my function always lies between those two bounds. And since both of those functions are approaching 0, as x goes to 0, that tells me that the function we're working with also has a limit of 0 as x goes to 0. All right, one place where the squeeze theorem is really useful is we can use it to actually derive some special limits. And so I want to show you a derivation for the limit as x goes to 0 of sine x divided by x equals 1. Now in this class, you can just memorize the fact that the limit as x goes to 0 of sine x over x is equal to 1. This is considered one of our special limits, and the next video is going to discuss this particular limit in a little bit more detail. But I wanted to show you a really nice proof of this fact using the squeeze theorem. So I'm going to start by drawing a unit circle. So that would be a circle with a radius of 1. And then I'm going to draw a ray in that circle, just sitting there in quadrant 1. And so if this is angle theta, the point that intersects my unit circle has to have an x-coordinate that's cosine theta and a y-coordinate that is sine theta. That's just the definition of our trig functions and the unit circle. Then I'm going to go ahead and draw a couple of vertical lines so that I have a total of 2 triangles. So I have a little triangle, I'm going to have a big triangle, and then we're also going to look at a sector of this circle. So let's start by looking at this little triangle right here in green. So this triangle, because it intersects my unit circle, has a vertex basically on the unit circle, I know that the height of this triangle is the y-coordinate on the unit circle. So the height of this triangle is sine theta. And the base of this triangle has to be the x-coordinate on my unit circle, which is cosine theta. So that's the first shape I'm going to consider, this green triangle. And then we can also look at this sector. So this is a portion of the circle, a sector of the circle. This sector has a radius of 1 because it's a piece of my unit circle. And then finally, I've got this big triangle in yellow. And this particular triangle, it actually has a height that's equal to tangent theta because I know that the base of this triangle went all the way across one radius of my unit circle. So the base of my triangle is 1. And then just based on the definition of tangent, tangent is opposite over adjacent. So tangent theta has to equal h divided by 1. That means the height, the h, is tangent theta. Okay, so I've got these 3 shapes within my figure, and looking at this picture, I can see that the area of the green triangle is going to be the smallest. So the area of the green triangle is always going to be less than or equal to the area of the sector, and that's always going to be less than or equal to the area of the yellow triangle. So I'm going to start with this inequality here. These 3 objects have areas such that, again, green triangle has the smallest area, blue sector in the middle, yellow triangle would have the largest area. And so let's actually come up with some expressions for the area of each of these shapes. Area of a triangle is 1/2 base times height. So my green triangle has an area that is 1/2 sine theta cosine theta. The area of a sector can be found by taking 1/2 theta times r squared. R is 1, so plugging that in, the area of this sector has to be 1/2 times theta. And then finally, the area of the yellow triangle, that would be 1/2 base times height, so 1/2 tangent theta. So I have the following inequality: 1/2 sine theta cosine theta less than or equal to 1/2 theta less than or equal to 1/2 tangent theta. And so let's actually work with this inequality and see if we can manipulate it to get the function that we're interested in, which was sine x over x, or in this case, if we're working with theta, sine theta over theta. Okay, so the first thing I'm going to do is just take my inequality and multiply everything by 2, just to get rid of those 1/2s. So now I have sine theta cosine theta less than or equal to theta less than or equal to tan theta, and we can rewrite that tangent theta as sine theta over cosine theta. Now, we're going to start by thinking about the fact that when we drew our triangles, we're in quadrant 1. So we drew all of our triangles in quadrant 1. So that's going to put a restriction on our thetas from 0 to pi over 2. So let's just keep that in mind. And then we'll consider another quadrant after this. But we're in quadrant 1 right now. And that's important because if we're in quadrant 1, theta is positive. And that means sine theta is also positive. So the next thing I'm going to do is I'm going to take my inequality up here, and I'm going to divide everything by sine theta. Because sine theta is positive, that's not going to change the direction of my inequalities. So I've got sine theta cosine theta divided by sine theta less than or equal to theta divided by sine theta less than or equal to sine theta divided by cosine theta times 1 over sine theta. And I can simplify this down to cosine theta less than or equal to theta over sine theta less than or equal to 1 over cosine theta. So this is almost what I want now. This theta over sine theta in the middle is the reciprocal of the function that I'm interested in. And in fact, if this inequality is true, cosine theta less than or equal to theta over sine theta less than or equal to 1 over cosine theta, because everything is positive in this inequality, I can just flip the inequalities and say that the relationship between the reciprocals of these functions has to be 1 over cosine theta bigger than or equal to sine theta over theta bigger than or equal to cosine theta. And so I have an upper bound and a lower bound now for my sine theta over theta, which is the function that I'm interested in. Now, in this problem, we're interested in what's happening as theta goes to 0. And so far, we're just considered what happened in quadrant 1. And so that would just be if theta is positive, so on the right side of 0. We do also need to think about what's going to happen in quadrant 2 on the left side of 0. But let's just go ahead and finish our quadrant 1 work. So if we're in quadrant 1, we're on the right side of 0. So I'm going to find the limit as x goes to 0 from the right of all of these functions. So limit as x goes to 0 from the right of 1 over cosine theta is just 1 over 1 or 1. And limit as x goes to 0 from the right of cosine theta is cosine 0 or 1. So now I know the limit as x goes to 0 from the right of sine theta over theta is equal to 1. Okay, so let's now do the exact same thing, but consider what's happening in quadrant 2. And that will give me my left-hand limit. That will tell me what happens when I approach from the left side of 0. So if I'm in quadrant 2, if I draw my triangle in quadrant 2, when I compute these areas, how I have written these areas or these expressions, there's going to be a negative quantity in them because sine theta is negative in quadrant 2. Theta would be negative and tan theta would be negative. And so what that's going to do is flip the direction of the inequalities. So if I make those areas negative, that's just going to change the direction of the inequalities. The shape that's going to have the smallest value of these expressions is going to be the biggest triangle because it'll be the most negative. So I've got the exact same set of inequalities. I just flip the direction of the inequality. And then I multiplied everything by 1/2, and I got sine theta cosine theta bigger than or equal to theta, bigger than or equal to sine theta over cosine theta. So I'm in quadrant 2. So again, the formulas for an area have a negative, so the inequality flips. So now I'm going to divide by sine theta. But since we're in quadrant 2, sine theta is negative, and those inequalities are going to flip yet again. And we're going to get cosine theta less than or equal to theta over sine theta less than or equal to 1 over cosine theta. This is identical to the inequality I had written down for the right-hand limit for the quadrant 1 case. So I won't repeat all of my work, but we can do the exact same reasoning. If we have this inequality, if we want to compare the reciprocals of each of these, the direction of the inequality is going to flip. So 1 over cosine theta bigger than or equal to sine theta over theta, bigger than or equal to cosine theta. We can find the limit of our boundary function. So we can find the limit as theta goes to 0 of 1 over cosine theta and of cosine theta. Both of those are 1. So that tells me my left-hand limit is 1, and therefore limit as theta goes to 0 of sine theta over theta has to equal 1. And I have a picture of what we've done with the squeeze theorem. In red is the graph of sine x over x. In blue is cosine x. And in green is 1 divided by cosine x, or secant x. And I can see that my red function is lying between the green and the blue one, and they are squeezing together. They all have the same limit of 1 as x goes to 0. All right, that is it for this video. Please let me know if you have any questions.